Thank you for coming to our session. This paper is about supporting inductive and interpretive text analysis with visual analytics. Say that 3 times fast. You might be more familiar with the terminology qualitative data analysis. To illustrate a use case for our tool, I wonder if you've ever been on a food blog website and noticed that all these recipes seem to contain flowery details about the bloggers' personal lives, and wonder to yourself, besides for search engine optimization, why are these stories so long? Has anyone studied this? What stories about interpersonal relationships or certain food items likely to elicit within recipe blog posts? And to answer this, you might scrape this website into a CSV file. And from an interpretive approach, analysis will entail manually coding excerpts on this data set and grouping those codes into categories. And you might use Google Drive to conduct this analysis, or fully fledged tools like MaxQDA. The point here is that interpretive approaches are manual and be very time-consuming. But at the very least, because it's manual and interpretive, we can ensure that human expertise is imbued in the analysis. Whereas algorithmic approaches to study text data using topic models or document clusters can generate insights automatically. That's Viz speak right there. But that's never the full story about machine learning. It still takes a human expert to interpret these models, validate them, and refine these models to ensure that they address the research question at hand. So in building our system, we speculated, what if we kind of inverted this paradigm? Instead of having a human in the loop workflow to analyze text data, what if an interpretive researcher sampled and coded documents, categorized those codes, and the model can then learn from their analysis, and the visualizations of those models can help users sample and code documents further, thereby placing the machine in the loop of qualitative data analysis. Our system comprises 3 views: the document map, which supports breadth-first exploration of the data set; the document reader, where the analyst highlights and codes documents; and the code examiner, which is used to iteratively refine codes and categorize them. Our system embodies 4 major design considerations. First is to support human expert induction, and the second is to have the model learn from the human's analysis, all the while using analytical paradigms that are familiar to an interpretive researcher, and finally overlaying those codes and categories onto the model visualizations. First, let's see how the document reader and the code examiner view support expert induction. Using the document reader, the analyst highlights and codes documents, and they also choose code keywords, which are a subset of the highlighted words that were the most semantically meaningful to this code. In the code examiner, the analyst then refines these code labels by revisiting previously seen documents in context. They can then also create and reassign categories for these codes. And here you see an indented tree depicting hierarchical word clusters generated from text data. And this is a prune tree that reveals only clusters related to those code keywords. So by clicking on each clusters at various levels of the hierarchy, the analyst can sample 30 documents that are the most potentially relevant to this code, again, in order to iterate on the user's ongoing analysis. And after a round of analysis, we will see how the machine can then learn from the user's codes and categories. As we saw, using the code examiner, the analyst refines codes and categorizes them. In the navigation bar of Scholastic, these codes are persistently shown, colored according to their categories. And here we will also find a button that says Update Clusters. Once the analyst clicks this button using the category tags, codes under those categories, and the code keywords, we then constrain how the words are clustered together and subsequently how the documents can be clustered together. And this entails running a community detection algorithm on this multi-layer network. This algorithm is thus interactive and hierarchical. And it adapts to users' ongoing analysis on their demand. It also outputs hard clusters instead of requiring the user to set a minimum probability threshold on topic models to output hard clusters. And it clusters documents along with words simultaneously. Once the models are updated, they can continue to sample documents using these models. So here we see the document view, document map view, where the colored pins indicate documents that have already been coded, and gray hexagons indicate documents that have been visited but not been coded yet. Using the step slider on the top left, I can adjust the granularity of the hierarchical cluster visualization, and also step through the evolution of these clusters as the model adapts to user input. And if they choose not to sample using the visualization, they can keep on sampling a random subset of the data. But using the map, right-clicking on the document shows a preview on the right, and left-clicking on the document takes the analyst to the document reader, where they can analyze its text. And we can see how all this works within an analytical paradigm that are already familiar to qualitative researchers. Even though existing interactive modeling tools can help users understand the data breadth and allow users to incorporate expert knowledge using interactions, they require that interpretive researchers to learn how to use these tools and work outside of their existing workflows where they label text data with codes. Whereas in our approach, the model learns naturally from the user's ongoing analysis using their codes and categories. Using familiar paradigms is also inherent in the visual design of our tool. Our document map draws a familiar visual metaphor to navigation maps, and the code examiner view draws a visual metaphor to familiar file folder structures. Lastly, we wanted to overlay codes and categories onto the model visualizations. To illustrate why this might be useful, let's go back to our illustrative user scenario. The research question here is, what stories about interpersonal relationships do certain food items elicit within recipe blog posts? Now, this is a question that actually requires multiple levels of analysis. So at the content level, the document clustering algorithm can help us organize all the meat recipes into one group and all the cookie recipes in another. And if the user finds that the top cluster tends to contain narratives mostly about feelings of warmth and community, and the bottom cluster tends to contain stories about family, it helps to be able to compare and contrast the model outputs, the codes and categories, and draw conclusions about the data, such as meat recipes tend to foster stories about warmth, and cookie recipes tend to foster stories about family. To summarize, in our tool, we executed the vision of placing a machine learning system within the loop of qualitative data analysis. And we accomplished this using an incredibly parsimonious input strategy, which entails the analyst coding documents, specifying code keywords, and categorizing codes, which one of our study participants noted that that's really a thing that they would be doing anyways. And in our paper, you will find a summary of outcomes from 2 qualitative researchers using our tool to conduct analysis. But to summarize directions for future research, we note that approaches to interpretive text analysis can vary widely. And this variance can be a function of the data set or as a function of the research question itself. And we envision that future system works supporting qualitative research using machine learning and visualizations. We'll be able to better adapt to these various user needs. Thank you to my collaborators and my former colleagues at the Atlas Institute, the University of Colorado Boulder. Thank you.
So for our Q&A,